This lesson deals with supplemental problem 321. You can find this problem in the ECE302 ebook in the Chapter 3 Supplemental Problems, starting on page 39. You can make an RS flip-flop, which is a reset set flip-flop, by interconnecting two NOR gates in the following way. The RTL version of this was taken from a magazine article in Radio Electronics in volume 58, number 6, entitled Working with Flip-Flops by Ray Marston. Given these RTL inputs of 0.2 and 0.2, 0.2 and 3.6, 3.6 and 0.2, and 3.6 and 3.6, can you find the voltage values for Q and Q bar shown above? I drew in for the NOR gate on top our RTL configuration of a NOR gate we had in the Chapter 3 lecture notes, where I've got a transistor, a base resistor of 450, and then a collector resistor of 640, and a battery power supply of 3.6. This is the top NOR gate where I had a Q output and an R input. And this is the bottom NOR gate, two transistors, two 450 ohms in the base lead and a 640 and a 3.6 volt power supply. And then my output was Q bar and my input was S. For these transistors, let's assume that VB on is 0.7, VCE sat is 0.2, and beta F is 100. Now suppose that I apply 0.2 volts to the reset line, and I apply 3.6 volts to the set line. What's going to happen? 0.2 volts here will cut off this transistor, and 3.6 volts here will saturate this transistor and make this 0.2 volts. With this being saturated, I don't have enough voltage here, I need at least 0.7 or more to get this transistor to saturate, so it's cut off also. So I have two open circuits here. At 3.6 volts, I've got a resistor, and then a PN junction. The voltage here, which is Q, is going to be equal to 0.7 plus the drop across this resistor. That's going to be 450 ohms times the current through it, which is going to be the difference of the voltages of 3.6 and 0.7 divided by this total resistance of 640 plus 450. And that's 1.9 volts. Logical 0, logical 1. Reset is 0, set is equal to 1. Q bar goes high. Anything bigger than 0.9 volts is logical 1. This is logical 0, the complement of it. We put a signal on the set line, we set Q high, and set Q bar low. And what would happen if we go from 3.6 then back to 0.2 volts? Well, now we're going to cut off this transistor. There's still this path of current to saturate this transistor. This stays the same, and likewise this stays the same. There's no change in the output if both R and S are now logical 0. But that's after the case of having set equal to 1 and reset equal to 0. Let me erase these and take a look at the next case. Suppose that we put a logical 1 on the reset line of 3.6 volts and a logical 0 on the set line of 0.2 volts. Well, the 0.2 volts, we're going to cut off this transistor. We need at least 0.7 to forward bias this. The 3.6 here is going to saturate this transistor. It's going to make this 0.2 volts. Making this 0.2 volts, we won't have enough voltage here, so this is going to be cut off. I've got two open circuits here. I've got a battery of 3.6, and I've got a resistor and another resistor back to a PN junction. It's exactly the same condition we had on the other side. This voltage here is going to be 1.9 volts by the symmetry in the problem. Putting a logical 1 on the reset line and a logical 0 on the set line, the output Q is set low and Q bar is set high. What's going to happen if we were to let this go back to 0.2 volts? Well, now we're going to cut off this transistor, but I still have this path for current. So the voltage here is still going to be 1.9 volts. If we go from reset logical 1, set to logical 0, and then go back to reset at logical 0, there's no change in the output, and that's shown below. Our first case and then our second case. Now suppose that we put a logical 1 on the reset line and the set line. Let's go back to the previous page. Let me clean this up again so we can put in those conditions. So now we're going to put initially a 3.6 logical 1 here and a 3.6 volt logical 1 here. Well, that's going to saturate this transistor. That's going to saturate this transistor. This is going to be equal to, because of the saturation, 0.2, our saturation voltage. And likewise here, saturating this is going to make this 0.2 volts. This being 0.2, I don't have enough voltage to forward bias this junction, so this is cut off. And likewise from this one. That would be cut off. We put a logical 1 on the reset line and a logical 1 on the set line. We now get a logical 0 and a logical 0. So Q and Q bar are not complements of each other. And we normally avoid this state in a flip-flop, but it can happen in an electronic circuit, and this is what's going to happen to the circuit. It's really not functioning as a normal flip-flop. Now the final state. Suppose that we let R and S be equal to 0.2 each. Go back to page 40 again and erase all this. That'll be covering our last possibility for inputs. Suppose now we put logical zeros on both the reset and the set line initially. That's going to cut off this transistor and cut off this transistor. With these two transistors, let me assume that T3 saturates. That makes this equal to 0.2. And with that being 0.2, this is going to be cut off. And I have that same path for current again, and this makes this 1.9 volts. And that was based on assuming that T3 saturated. What if T2 saturated? Let's erase this, and erase this. If T2 saturates, that's going to make this 0.2 volts. That's going to make this cut off. And I'm now going to have a path for current coming this way, creating a voltage here of 1.9 volts. And again, this was assuming that T2 saturated, and that forced T3 to be cut off. I have two different answers depending on which one I assume first. Both are possible. We can't predict what's going to happen. Let's go back to page 41. This is the case we just described. We can summarize everything in a table. Here's R and S, two logical zeros, logical 0, logical 1, logical 1, logical 0, two logical 1s. Put a logical 1 on the set line as logical 0 on the reset line. The output Q goes high and Q bar goes low, and then vice versa. Put a reset logical 1 and a set logical 0. We reset the output to logical 0 and the complement to logical 1. If we put two logical zeros in, given a previous state, we can then predict that there'll be no change. But if you do this initially, we don't know what's going to happen. And lastly, if you had two logical 1s in, we have an inconsistency with Q and Q bar. They're both logical 0. So we avoid this state in using the flip-flop. And this is supplemental problem 321.